moving to the next session, I would like to introduce you to the next speaker, Dr. Taehui Na. Dr. Taehui Na is an assistant professor in the Department of Electronics Engineering at Incheon National University, South Korea. Dr. Na completed his BS and PhD in Electrical Engineering from Yonsei University, South Korea. Before joining INU, he worked as a staff engineer at Samsung Electronics. He's the head at Samsung VLSI Circuit Design Laboratory at INU, South Korea. He's authored 23 international journal publications and has been issued 24 US patents. His areas of research interest are PVT variation tolerant and low power circuit design for memory and MCU, ultra power analog front end and back end circuit design for IoT applications, and high security level design for MCU. May I request Dr. Na to please deliver his talk. Over to you, sir.
Thank you. Thank you for a kind introduction to me, the Vasundhara, and also I'd like to say thank you for the organizing members to arrange and the host this workshop and to give me the opportunity to give my talk. Okay, and I also say thank you for the previous speaker, the Dr. Mbika, addressing the PVT variation, because my talk is also quite related to this reliability issue. Okay, now I will share my document. Actually, I'm not quite familiar with using this WebEx, so if there is problem, please tell me. Okay. Okay. Now my document is shared. Okay. So again, my name is Taehui Na, the professor in the Incheon National University, and the title of my talk is, wait a second. The title of my talk is STT-MRAM and its sensing operation for the low power IoT applications. Well, I think maybe you are not very familiar of this STT-MRAM. So before starting to explain about this talk, I will briefly explain about STT-MRAM. Well, you can easily think that STT-MRAM is the emerging non-volatile memories that is considered as the very promising candidate. Okay, and I will explain later in detail. And because I have already been introduced, so I will skip this slide except for my career. Well, during the PhD course, I had worked with Qualcomm company located in San Diego, USA, and mostly I dealt with STT-MRAM circuit design. So that's why today's title of this talk is related to STT-MRAM sensing. And after receiving the PhD degree, I entered the Samsung Electronics, and mostly I designed on the phase change random access memory, read and write core circuit design, and high performance NAND flash memory. Okay. Well, I will start. Let me start my talk now. And as all of you may know, the current semiconductor technology has been driven by technology scaling. And it is obvious that technology scaling enables cost reduction and architectural innovation. This figure clearly shows these advantages. Let's see together, but I will go quite faster, okay? Well, this slide shows that the technology node of the 32 nanometer is scaled down to 20 nanometer, and again 14, 10, 7, 5. In this case, the scaling factor is 0.7. Okay, so if we consider that this length is 1 and 1, the next technology node is 0.7 and 0.7. Very clear. So what is the area in this square? It is 1, right? 1 times 1. In this case, each area is almost 0.5. What it means? It means that same circuitry can be integrated only in the half space, or we can integrate twice the circuitry in the same space. So obviously, cost reduction and architecture innovation can be achieved. Okay, and not only the economics of the semiconductor technology scaling, but also there is other benefits such as high performance and the low power. And these kind of advantages have boosted to use more IoT devices. So you can see that as time goes by, the number of devices used around the world has been increased exponentially. And interestingly, 2008, the number of devices connected around the world uh, was increased more than the world population, and because the IoT devices or the wearable devices are made of the semiconductor, so and also all the information extracted from the IoT devices need to be stored in the memory semiconductor. So at the same time, the growth of semiconductor market has been increased. Okay, so I'd like to ask a question. What is the key drivers in the current semiconductor market? The answer is obviously information. So to process more data, to process more information nowadays, processor and softwares are being developed. And to store more data, more information, our storage technology and the memory technology has been developed and improved. And where this kind of information come from, of course, is from your mobile devices, wearable devices, and a variety of IoT devices. So nowadays, processing, storage, and acquisition, these are a very important topic. But in this talk, I will focus on the storage part, memory part. Okay. Okay. At this time, I'd like to address the definition of the memory. What is memory? The first you need to know, because I am really familiar, and as a South Korean, because as you know, the Samsung Electronics and SK Hynix are the big tech company when it comes to the memory semiconductors. So I'm very familiar, but you may not familiar about it. So I'd like to give some information about the memory. Well, in the modern computer architecture, there are two main parts. The one is processor. It could be the central processing unit in case of your desktop, or application processor in case of the mobile device. And there is another part, which is memory, right? In case of processor, what is the major role? The major role of processor is to calculate something data, right? And what is the memory? Actually, memory can hold and read and write data. The computing data in the processor need to be stored, need to be written to the memory. This operation is called write operation. And during the standby mode, let's think about the IoT devices. The most of the IoT applications, their most lifetime is measured by the standby mode, right? So all these computing information need to be stored in the memory, and these memory need to be held during the standby mode. This operation is called hold operation. And again, let's think about it. Our IoT device the IoT device mode has been changed from the standby mode to the active mode. In this case, processor need to read the data from memory to the processor. This operation is called read operation. So memory can hold data, read data, and write data. This is the major role of the memory. Well, nowadays, there are the many types of commercially available memories. This slide shows the three representative memory devices: SRAM, DRAM, and the flash memory. SRAM stands for static random access memory, and this figure shows the 1-bit cell circuit diagram of the SRAM. This symbol means the inverter composed of a single PMOS and a single NMOS, right? So you can easily think that the six transistor makes one SRAM B cell. So 6 transistor means quite a large number of transistors for storing one bit. So you can easily think that SRAM memory is the fastest memory, but the most expensive memory. Well, at this time, the static means according to the time, the data stored in this memory is not changing. It means, well, for example, the Q could be 1 and the QB could be 0. So by using this structure, it can store just one bit. In this case, because of the power supply connected here, so the value 1 or 0 will not be changed according to time. So it is called static random access memory. Unlike the static random access memory, the second type of commercial memory is the DRAM, the dynamic random access memory. The DRAMs, the 1-bit cell is composed of 1 transistor to 1 capacitor to store 1 bit by using the charge Q here. Well, in case of DRAM, it is a dynamic random access memory. Dynamic. So dynamic means this charge or the stored data, it could be 1 or 0, can change according to the time because of the leakage current. Right? And the leakage current is becoming worse as the technology node scales down. So in case of DRAM, the periodical refresh operation is required. And both SRAM and DRAM are volatile memory. It means the data will disappear if there is no any power supply. Let's think about it. If there is no refresh operation, this charge will disappear, right? And let's think about it. There is a power supply VDD, and if we turned off the system power, so VDD becomes 0 voltage, then our stored data will disappear. So it is called the volatile memory. Unlike this volatile memory, the flash memory has the non-volatility characteristic. It means without any supply power, the data can be stored, can be maintained. The flash memory uses the floating gate. The charge can be trapped, stored in the floating gate using FN tunneling. Okay, this is the brief summary of the commercially available memories, and let's move on the memory development trend. Well, nowadays, the number one, the memory development trend is the low power, obviously. Nowadays, low power is the most important topic around the world. Not only the mobile device or the wearable devices, which are the battery powered devices, because in case of battery powered devices, the battery lifetime is the most important thing, right? Also, nowadays, the data center consumes a lot of power. So nowadays also reducing the power consumption in the data center is really important. Of course, to achieve the carbon neutral, right? So let's see this circuit diagram. Well, it shows just one PMOS and one NMOS, and it is the inverter and two inverters connected together. Well, it is the basic building block of the digital circuit. And in case of digital circuit, the switching power can be expressed like this way. The load capacitance times power supply VDD square times F. You can easily derive this equation through using these equations. It means if we reduce the power supply, then power consumption can be quadratically reduced. And if we reduce the technology node, which is the minimum channel length, it means the loading capacitance can also be reduced. So this figure shows the DRAM technology trend when it comes to supply voltage and the technology node. So okay, so DDR number one, the used power supply was 2.5, and it has been scaled down to 1.8, 1.5, 1.2, and in case of DDR5, it reduced to 1.1 voltage. In case of DDR5, it will be commercially available at the end of this year. And at the same time, the technology node has been reduced from 110, 60, 30, and in case of DDR5, it uses 14 nanometer technology with EUV equipment, okay? And the trend number two is high performance. Well, this y-axis means the I/O speed per pin in DRAM, and the x-axis shows the year. So this picture also clearly shows that as time goes by, the performance has been increased to achieve the demand for fast processing of more data nowadays. And the another trend can be high density. Well, the high density memory is obviously the NAND flash memory, right? So in case of NAND flash, to achieve more density, multi-B cell has been used. So it shows the single level cell. It means for one transistor, the one bit can be stored. It has been evolved to multi-level cell. 2 bits can be stored in one transistor, and three bits can be stored in one transistor. And nowadays, QLC, quadruple level cells, is now available. And also, previously, there was the 2D scaling. It means that it is the same as the Moore's law, the technology scaling. However, it has reached the limitation at around 20 nanometer. Actually, there was the test that in the Samsung Electronics, and at 14 nanometer technology, they found that it is not cost effective, and there are so many other side effects such as the cell-to-cell interference. So they stopped 2D scaling and they changed it from 2D to 3D scaling, like the vertical scaling. So nowadays it is available for 128 layers 3D, the vertical NAND flash memory. And another way to increase the high density is to use the through silicon via TSV in the high bandwidth memory like this. Okay, so briefly we have seen the three major trends: high performance, low power, high performance, and high density of the memory technology trend. However, in the current the common memory system, there are some problems. I'd like to address some problems briefly. The problem number one is memory wall. Well, you can see a kind of pyramid. This figure shows the memory hierarchy. the register, the level 1, the level 2, level 3 cache is composed of SRAM. SRAM, and there is a DRAM and the flash storage. It is most usually used the USB drive, or the SSD, and the hard disk drive. Well, you can easily think that the higher, the more faster, however, more expensive. And if you think about the IoT devices, the computing data need to be transferred from CPU to the flash storage through the DRAM. However, unfortunately, in the current memory system, there is a big performance gap between the CPU to DRAM and the DRAM to flash storage. So it is very inefficient, and the overall system performance and the power is now governed by the memory system rather than the CPU system. So how can we overcome this problem? Actually, the simple way is to add more layers by using another the class memory. However, this remedy is generally very expensive, so it is not possible. So a fundamental way to overcome this memory wall problem is to modify the memory system by using a unified memory that has the characteristic of high performance, high speed like SRAM, quite good or decent memory density like DRAM, with non-volatility like SRAM. If there is this kind of new memory exists, the computing data don't need to be transferred from the SRAM to the flash storage. The one candidate of this kind of new memory is STT-MRAM. So I will discuss. That's why I am addressing this kind of issue. And another problem is obviously SRAM leakage current. Well, nowadays, in a processor, the number of cores has been increased, and interestingly, the SRAM leakage is increasing as time goes by, and also it is exacerbated as the technology node scales down. And at high temperature, this leakage power is becoming worse. This figure shows very interesting result that in 2023, the leakage current at 50 degrees Celsius can reach 2 ampere. Let's think about your mobile phone's battery capacity, mostly on the order of 2000 mega ampere hour, right? Or in case of my mobile phone, which is the Galaxy Note 10, in this case, it is 3500 order, but the order is the same. So if you imagine that your mobile phone battery has been fully charged and just remains without using anything. In this case, after 1 hour, you can see that your battery percentage could be 0% because of just leakage. So it is a really big problem. And in case of SRAM, at advanced nodes, it is becoming more expensive. The example is like this. At 40 nanometer technology, the 60 SRAM 1 bit cell area is around 150 F square. You can easily think F is equal to the technology node 40 nanometer. However, when it goes to the 7 nanometer technology, the SRAM's 1 bit cell area need to be increased to 550 F square. In this case, F is 7 nanometer. So it means it is becoming more expensive. So we need to address this problem, and we need to consider the new perspective on energy efficiency. Well, you can refer to this kind of information recently updated. The smartphone, smartwatch, fitness tracker, hearing aid, battery capacity. And now let's see about this figure. The common memory subsystem for the microcontroller unit and the IoT applications. Well, as a brain, there is a CPU. And for the high performance memory, there is SRAM. And for non-volatile memory, there is the embedded flash memory, or external the flash memory. In case of SRAM, as I mentioned before, there is a leakage problem, and it is the volatile, right? In case of embedded flash memory, it is slow and it requires high power consumption. And it is worth noting here that in case of embedded flash, it is not scalable less than 28 nanometer technology. And also, it cannot use the FinFET technology because it is not the cost effective anymore. Okay, and in case of external flash, slower, higher power, and insecure. So there is a need for an unified memory system that is able to overcome these inherent shortcomings of eFlash, external flash, and SRAM. Okay, now let's briefly see about the memory classification. In case of memory, there are two types, as I mentioned before, the volatile and non-volatile, right? Well, you can easily think that in the yellow box, it is the mature, the mainstream memory devices. And the green box, it is the emerging and currently in the small market devices. So the mainstream device is SRAM, the DRAM, and flash, as I explained before. And in case of non-volatile memory, there are two types, charge-based and resistant-based. In case of resistant-based, there are phase-change memory, magneto-resistive random access memory, and resistant random access memory. And I will focus on STT-MRAM. Actually, SRAM, MRAM, each target application is to replace the last level cache or embedded flash. And in case of PC RAM and RRAM, each target application is to replace the storage class memory, such as SSD. And it is the old version of the MRAM, and it is immature, so it is now very popular. The memory device, emerging memory device, that is a promised candidate to replace the SRAM plus embedded flash, the combination. Well, this slide shows that some compares the table of the various memory types. In case of embedded flash, as I mentioned before, it is not applicable to the FinFET technology. And in the NOR flash, it is very slow. In case of PRAM, also it is not easy to use the FinFET technology, and PCRAM and RRAM, each endurance is not good. So MRAM, STT-MRAM is the best solution for FinFET embedded non-volatile memory due to cost and application coverage. Well, I need to move more fast. So there are many applications, and you can see this block diagram that SRAM and eFlash combination can be replaced to embedded MRAM. And in this case, there are many advantages like chip size, battery lifetime, standby power, cost, except for active power. In this case, active power is related to the read power consumption. So not only the industry like Samsung Electronics, but also academia are trying to reduce the read operation power as close to the SRAM cell does. Okay, now let's move on to the main topic, which is the STT-MRAM and each sensing operation. Well, not to be confused about the terminology, I'd like to explain in advance that the MRAM MRAM terminology stands for magnetic resistive random access memory. Sometimes it is used magnetic random access memory. And in case of spin transfer torque, it is called frequently STT-MRAM or ST-MRAM or STT-RAM. Okay, and because of the limited time, I will deal with very briefly about the sensing operation. So if you want to get more information, please refer to this paper, published this year, January. Okay, well, because MRAM uses a spintronic device, I'd like to introduce a spintronic device at first. Well, so far, both transistors have been used as just the on-off switch, right, for logic and memories, which form the foundation of modern computing. As technology node scales down, there was some scaling challenges, such as the increase in the leakage current or the on-off current ratio decrease, or the short channel effect, or the voltage variation. So the spintronic device, which utilizes the spin of the electron as a state variable for computation, has emerged as one of the leading candidates as post-CMOS technology. Well, you can easily think about the spintronic device that has two states. Let's think about this picture. You can easily think that spintronic device could has upward spin magnetization direction and downward magnetization direction, and between the two states there is a barrier. And because of this barrier, this device can have the characteristic of non-volatility. Okay, so by using this state, we can use the spintronic device as a memory device to store the distant value 0 or 1. And in case of switching or the right operation, you can easily understand by using this picture. Let's think about this. This device is our spintronic device having the upward magnetization direction. And there is an instant electron having the magnetic direction of this direction. If this electron passes through our spintronic device and the transmitted electron's magnetic direction becomes upward. However, because of the conservation law of angular momentum, in the opposite direction, there is a torque inside of our spintronic device. So this transmitted electron, it gets the torque in this way, and in our spintronic device, the torque is in this way. So if this torque is greater than some threshold, then this upper arrow can be changed to the downward. So it is the simple explanation of the switching or the right operation of the spintronic device. Well, there several merits: non-volatility, fast switching, small size, unlimited endurance, but I will skip. And in the system level, if the SRAM cache is replaced to the STT-MRAM cache, these two papers have shown that 80% power can be saved, or the 64% energy can be saved with negligible performance degradation. Okay, and there are many types of spin tuning device. For STT-MRAM, we used the magnetic tunnel junction. Okay, let's see here. Well, in case of magnetic tunnel junction, the MTJ, there are the pinned layer, reference layer. It means this magnetization direction is fixed, not changeable. And there is the free layer. In this case, magnetization direction can be changed. So if we make the parallel or the anti-parallel, so in this case, we say it is the state 0 because it has the low resistance. And in case of anti-parallel, we say state 1 because it has high resistance. Okay, very simple. Okay, so parallel, low resistance, anti-parallel, high resistance. So please remember RL and RH. Well, and this figure shows the simplified the memory, the structure, having the array, reference array, and the Belite MUX, Waterline MUX, sensing circuits, and amplifier. By using the Belite switch and the Waterline switch among this array, we can choose only one selected cell, and according to the data stored in this one bit, it can be converted using the sensing circuits and amplifier. So this stored data can be transformed to the digital signal 0 or 1. It is the major operation of the memory. Not only the STT-MRAM, but also any other memory, such as DRAM, SRAM, flash memory. All memory architectures are very similar. And in case of STT-MRAM B cell, it is composed of one MTJ and one transistor. And to write, okay, well, it would be better to skip the write operation. So just remember that in case of STT-MRAM, the current induced magnetic switch. So by applying the current from the B line to source line or source line to B line, we can change from this way to this way. So it can change from the low resistance to high resistance. Very interesting characteristic of the STT-MRAM is high scalability, because in the critical switching current, in the write current, it is proportional to the MTJ size. It means according to the technology scaling, if the MTJ size is decreased, the required critical switching current is also decreased. So it is really the high scalable. Actually, there is some side effect, such as the read distance problem. But in this kind of case, we can overcome by using some circuit technique or architectural innovation. Let's see this figure together. Well, this is a transistor, both, right? The gate, source, drain, and the MTJ can be placed in the back end of the line process. So this is the metal 1, and this is the metal 2. So like a via, MTJ can be placed between the metal 1 and metal 2, or it could be between the metal 3 and the metal 4, something like that. It is different according to the companies, but the major principle is the same. So it's very very it does not increase any area overhead, and it is very compatible to any other technologies such as bulk, SOI, and the FinFET. Okay, I think I have only almost 15 minutes, so I need to run more quickly. I'd like to deal with now about the sensing margin issue of the B cell itself of the STT-MRAM. Well, this is the MTJ spintronic device, and you can easily think that in case of low resistance, each resistance value is in general 3 kilo ohm, and in case of high resistance, each resistance value is 6 kilo ohm. After sense amplifier, 3 kilo ohm need to be converted to the digital signal 0. And in case of 6 kilo ohm, it needs to be converted to digital signal 1. 1 means VDD, and the 0 means ground, right? How it is possible to distinguish between the low resistance and high resistance? The reference register is required, which is exactly the half between the RL and RH, which is 4.5 ohm. And in this case, because of the power budget and not to make the relative disturbance, the maximum all-over current value is 20 microampere. 20 microampere. So let's just think about the voltage value. The resistance is 3 kilo ohm, 4.5 kilo ohm, and the current is 20 microampere. And if we use the Ohm's law, the V is equal to IR. In this case, this node voltage, beeline voltage, is equal to 60 millivolt, which is I 20 milliampere times 3 kilo ohm. In this node, the redundant beeline voltage, in this case, it become the 90 millivolt. So only the difference between beeline voltage and beeline bar voltage is 30 millivolt. In case of RH, it is the same, 30 millivolt. Do you think it is enough to change this voltage difference to digital signal? Actually, it is the minus 30 millivolt and it is plus 30 millivolt. In the viewpoint of the read yield, with considering the input referred of the voltage of the sense amplifier, mostly the input referred of the voltage of the sense amplifier is in the one standard deviation is mostly 20 millivolt. So if we calculate the read yield, then each result is only 1.5 sigma. However, in the industrial level, this read yield must be greater than 5 or 6, or if we are not using any ECC engine, then it need to be greater than 7 sigma. So to increase the read yield, mostly we need to utilize sensing circuit as a preamplifier. Without sensing circuit, in this topology, read yield is only 1.5 sigma. Okay, so now let's briefly see the conventional sensing circuit and the improved version of the sensing circuit. So now it is the circuit technique. Well, if we see about conventional sensing circuit, if we see this circuit diagram, maybe if you are quite familiar to the circuit design, then you can easily see the operation of this circuit, because it is very similar to the basic circuit diagram. of the common source amplifier that you've learned in the microelectronics class, in the undergraduate class. So you can see that there is the R data. It could be a 3 kilo ohm or the 6 kilo ohm. And in case of RF, ideally it could be 4.5 ohm. And it is the sensing circuit as a preamplifier. And you can see that there is the NMOS, and you can easily think that there is a load resistance, RD, and it is the transistor. Let's remind about the common source amplifier or the common gate amplifier. Common source or common gate amplifier, RD, and V in, V out. What is the gain in the small signal? What is the small signal gain? We know that small signal gain is GM RD times V in, right? The operation is very similar this circuit. So this PMOS is called the load PMOS, and this transistor is called clamp PMOS. And we can analyze this circuit diagram using the mathematical operation. However, using the graphical tool is much easy, and it gives much more insight. So I'd like to introduce the load curve analysis. Y-axis shows the current, and x-axis shows the voltage. Okay, and when we see at this point, then when the R data is RL, then the IV curve can be drawn like this. This is this green line. If R data is RH, it can be drawn like the pink color. And if the RF can be drawn like a blue color line. Now let's think about this transistor. In case of load transistor, gate and the drain are connected together. So we say this kind of structure, the diode connected. So because of diode connected, each IV curve can be drawn like this. And because this gate voltage is shared to the data path load PMOS, the data path load PMOS IV curve can be drawn like this. Actually, if you are not familiar of dealing with this kind of load curve analysis, you may feel very difficult of understanding of this analysis. But if you invest a little bit more time to understand about it, then you can easily understand, and it could be really, really, really important tool. Then nowadays and later you can utilize in your research topic. So if we use this kind of load curve, and we can easily find the upper voltage of the sensing circuit graphically. So this node voltage is the V data, and this node voltage is VREF. And you can see that this is the V data 0, this is the VREF, and this is V data 1. You can see that in the graphically, we can easily find that this delta V is now greater than 200 millivolt, right? Previously, in the theoretical, the delta V was only 30 millivolt. However, by using the preamplifier, it has been increased to greater than 20 millivolt. So it can overcome the input referred offset of the sensing amplifier. And it is the conventional sensing circuit, and a little bit improved version is to add this transistor. This is the source degeneration. Source degeneration is also very popular circuit technique by adding a resistor in the source side. We can increase output resistance significantly by using the cascade operation, right? So if we increase output resistance, then we can increase the sensing margin. So it is the another simple technique to improve the sensing margin. Well, however, in this case, what could be the problem? Actually, as the previous speaker mentioned, there is the pivot variation. So in this case, the critical factor degrading the sensing margin is the mismatch between this transistor and the mismatch between the two transistors. It is the local variation actually, mostly caused by the random dopant fluctuation. So to overcome this kind of problem, I'd like to introduce two offset tolerance sensing circuits. The number one is the name is this, and the advantage, it has the two advantages. Number one is offset cancellation, and the number two is the double sensing margin structure. Well, okay, it would be better to use this slide to explain about this circuit operation. Well, the concept is really simple, okay, so you can follow very easily. In the first stage, the operation is like this. This circuit is exactly the same as the conventional sensing, right? So it is connected to R data, it is connected to R ref, and this voltage is the data voltage. It is the first stage by just using the source degeneration circuit. In the second stage, however, by using the another switch selection box, it is kind of chopper in the analog device, instrumentation amplifier. Okay, so by adding the another switch, so this clamp transistor is connected to reference, and this clamp transistor is connected to R data. It is the main concept of this circuit to generate the reference voltage. What is the advantage of this circuit? The number one is offset cancellation. Offset cancellation, okay? Because to generate the data voltage and the reference voltage using the same node. So effectively, offset can be compensated. Offset can be cancelled. And the second advantage is, well, is the conventional sensing structure, right? So there is a current mirroring. So if there is this RF and the RF is current mirrored, right? And there is I cell, and in case of V data, if IRF is higher than I cell, this voltage can be increased. If IRF is smaller than I cell, this voltage can be decreased. This is the main operation of the conventional sensing circuit. So the delta V can be expressed by using the upper resistance of the load PMOS times current difference. In case of this circuit, V data and V ref can be expressed like this. And finally, delta V can be expressed like this. 2 times upper resistance times current difference. So double sensing margin can be achieved. So very simple technique, but the improvement is very significant. So this slide shows the distribution of the delta V. In case of this distribution, you can see that it is quite wide because of the process variation. By using a simple offset cancellation technique that does not have any double sensing margin characteristic, in this case, that delta V distribution became very narrow, but delta V is low. However, by using the double sensing margin structure, you can see that the delta V has been doubled with narrow distribution. And there is another offset tolerance sensing circuit having not only the offset cancellation and double sensing binding structure, but also strong positive feedback. However, because of limited time and also in case of this circuit, the operation is quite complex to explain. So it needs a lot of time because it contains the cross-coupled HEMO structure with cap. So I will skip. So for more information, please refer to this paper. And so far, I explained about the sensing circuit. And the another part is the sense amplifier. Well, I try to introduce just a brief, very widely used sense amplifier. There are two types of sense amplifier. The first one is current latch sense amplifier. This kind of type is current latch sense amplifier. And this type is called voltage latch sense amplifier. The only difference is, well, in case of current latch sense amplifier, input and output are separated, isolated. So there is no any the noise. There is no any noise from input to output or output to input. However, in case of VLSA, input and output are connected together. In the viewpoint of the performance and area overhead, VLSA, this kind of amplifier is better. So mostly, it is recommended to utilize this sense amplifier. However, if some reference voltage is very sensitive to noise, then I would like to recommend for all of you to utilize this type, CLSA. Okay, because almost the time's up, so I need to move to the next section. Well, so far, the many big tech companies have already demonstrated the STT-MRAM prototype. Please refer to this slide and commercially available. So Samsung 28 nanometer in 2019, and this is the GPS smartwatch chip employing the embedded STT-MRAM 1 megabyte. Okay, and the also TSMC, Everspin, and Intel is also preparing. Okay, this is the characteristic of the STT-MRAM, and I will skip the introduction of my lab. Okay, that's all. I will finish, and thank you for attending my class. Thank you.
Dr. Na, I mean, if you wish, you can speak a little bit about the previous 3 slides, because after this there is no session. And I feel that people will, yes, incomplete memory or something like that, yes.
Oh, okay, it will be better.
Because
So,
we have another 4-5 minutes we can spend on these quality slides. Before this, I think you have incomplete memory or something like that.
Oh, okay. Actually, the goal of my lab is to achieve the low power and the smart IoT. If we see the IoT node, the basic building block can be explained like this. So there is a sensor, and there is the microcontroller unit which acts as the brain of the IoT node, and there is RF for the wireless communication. But if we break down the power, then you can see that in case of IoT application, standby power is the predominant 66%, right? Because mostly operated in the SLAM mode. So the number one goal is to utilize the non-volatile MCU. So it is the current conventional MCU, flip-flop cam, CPU, cache memory, main memory, storage. If we replaced the volatile memory to the non-volatile memory, such as non-volatile flip-flop, non-volatile cam, non-volatile memory, then we can eliminate the standby power, increasing the battery lifetime. That's the number one, the primary solution. So today's talk was related to STT-MRAM only. Okay, and if there is a chance, then I will explain other part. And let's skip. And another primary solution is to achieve the ultra low power reader circuit design. So it is just an example. The wearable patch. From our body, we can extract a lot of biosignals such as the ECG, PPG bioimpedance, and the temperature. And it can be processed. It can be extract by using the ultra low power instrumentation amplifier such as the analog amplifier, and it can be processed using the digital backend circuit and the wireless communication. So these are the examples that I have designed previously. So this is another topic to achieve the low power reader circuit design. And the final, the primary solution is the computing in memory. Nowadays, as maybe all of you may already know, the von Neumann architecture has the bottleneck for the movement of the data between the CPU and the memory. And a very promising candidate to overcome this problem is to utilize computing memory as a neuromorphic computing. And my research lab also planning to research about this topic in the near future. And okay, that's all. Thank you for giving me some time.
Thank you, Professor Na. Over to you, Narendra and Shundra.
Yeah, thanks, Dr. Na. So it was a wonderful talk. So I am also working on the in-memory competence. So I have one question regarding a sense amplifier. In one of your slide, you mentioned that there is 30 millivolt sense margin. You mentioned. So my question is how we can fix the sense margin for any sense amplifier, on which physical parameter it depends for analog computation.
Can you tell me one more time about your question? I didn't understand.
Yeah. How we can fix the sense margin, that is you mentioned 30 millivolt, on which parameters? Yeah. If we want to vary from 30 millivolt to 50 millivolt, then which parameter we have to make?
Of course, it's not possible to fix the sensing margin because to simplify the explanation, I ignored almost all other parameters such as the parasitic resistance and parasitic capacitance, and also the process variations of the transistor. For example, if we look at this one transistor, one empty B cell, to achieve the 30 millivolt sensing margin, we have to ignore this transistor, right? However, if we add the transistor, sensing margin is decreased significantly, and it is also related to the waterline voltage. And if we add the parasitic resistance, because in this memory array, each array size is really huge, so there is a significant amount of beeline resistance, beeline capacitance, and there are a lot of switches such as beeline, source line, waterline, and to connect sensing circuits and sensing amplifier. All these kind of factors influence on the degradation of the sensing margin. So actually 30 millivolt is the ideal sensing margin, but in the real case, each voltage is decreased significantly. Yeah, so my opinion is it is not possible to fix the sensing margin. The simple way is to increase the transistor, the bigger. However, there is a trade-off between the array efficiency and the cost price. So yeah, it is not a good solution. So we need to think about in the device level, the device designer need to improve the resistance ratio between the low resistance and high resistance as much as possible. And as a circuit designer, we need to come up with a new way that is able to ignore the other side effects, such as the process variation of the transistors. Yeah, that's all. Thank you.
Hello, hello, Professor. I have one question. Like, if we think about the HBM, and if we think about again the STT to use in the HBM, so as we are all aware, like in the HBM, mostly the problem is a heating effect inside to the layer that. So how we can tackle the problem that heating effect through that STT? Like, what are the property which is come up with the STT which might be the better in comparison with the other devices in case of HBM implementation?
Well, when it comes to the HBM, it is used for the DRAM. So in case of STT-MRAM, it is not available. See, actually, but my opinion about the thermal problem is, well, in the industrial level, because I have experienced in the Samsung Electronics for 2.5 years. In this case, in case of a heat problem, I heard that the heat problem is not very significant now. So in the academia, we are concerning about the heat problem, and it could be very significant factor that is able to degrade the performance of the chip performance. However, it is very dependent on the data workload, right? So if we are using the read intensive workload, then it could be the heat problem. But in the most other the workload cases, there is no any heat problem, as far as I know.
And again, one more question, Professor. In the slide number 27, if we see the VI characteristics as you mentioned over there.
27.
I think, yeah. So here, if we see that VI characteristics, so distance between like that for the RL value, RH, RL, and the supply resistance. So if we see the distance between these three lines is nearly equal. So can we consider there is a linear effect of resistance, or is there any perception we should take from this VI characteristic? Like, I mean, if we see in the InMOS, I mean, in the MOS devices, there is a distance between the VI characteristics get increased with the VGS value. But here we look at it is like distance is quite similar. So is the linear effect of resistance in the current?
Linear effect of the current?
Yeah.
Actually, I didn't understand what is your question exactly. But if I wait a second. Well, if I give my answer is that well, mostly the resistance, the MTJ resistance is linear. But if we see this the IV curve, it shows non-linear, right?
Yeah.
Is basically because of the transistors operation, NMOS transistor operation. So according to the drainage source and the gate voltage region, it could be operated in the linear region, or it could be operated in the saturation region. So,
and means my question was
not correct. Okay.
Yeah. So if you see that characteristics, there is green line, blue line, and the third one, which like three current lines are there. In which, if you see the distance at the end, like at 1 volt, if you see the distance between these three curves will look similar.
Distance between the green and blue, and the distance between blue and pink.
Yeah.
You mean?
At 1 volt, it looks similar distance. So can we consider there is a linear effect of resistance, or?
Yeah, right. Because only the difference is the resistance. In this resistance is 3 kilo ohm, or 4.5 kilo ohm, or 6 kilo ohm. According to this resistance, this current value changes. So it is linearly different. Actually, because this resistance is at the source side of this NMOS. So actually, it is not linear exactly, but we can easily analyze that. We can easily think that because of the linear factor, this current difference is similar. Yeah.
Okay. Thank you.
Is there any more questions? So in case anyone has any question, please ask. It's a good opportunity that professor is here. Professor, you can see some question in the chat box.
Oh, okay. I didn't check the chatting
please.
box. Okay, wait a second.
In case you have time.
Oh, I have a lot of time today, of course.
Thank you.
IoT devices, which tech node should be more usable node with respect to commercial and the design perspective? For this question, I'd like to say that nowadays, actually, in case of the low-cost IoT application, the old technology could be selected because it is much cheaper. However, as a consumer, the end user, we requires the higher performance. So many IoT devices need started to move to the advanced technology node, employing the FinFET technology, right? And one example is the recently released the Galaxy Watch 4. Galaxy Watch 4, released by the Samsung Electronics. They employed the 7nm technology AP. So yeah, the advanced technology node, it means high performance but low power, obviously. Another question is, okay, I think that there is only one question in the chatting box.
हाँ संतोष सर
भाई साहब मैं आपको 5
there is
मिनट फोन करता हूँ, ये समापन चल रहा है अपने प्रोग्राम का।
Okay, if there is any question, feel free to ask to me.
Can I ask one question?
Oh, yes, of course.
So first of all, so I really appreciate your enlightening talks as per the STT-MRAM. Particularly, my question is what is the key limitation to improve the memory density based on the STT-MRAM as compared with the previous non-volatile memory scheme? I mean, in particular, the material aspects or the design aspects. Could you comment on that?
Well, if we compare the STT-MRAM with other non-volatile memories, such as maybe you are quite familiar of the other emerging non-volatile memories, such as the RLAM or the phase change random access memory, right? The target application is very different. In case of RLAM or the phase change random access memory, their major target is to replace the SSD, the NAND flash memory, or aggressively to change the DRAM, right, for high density memory. The reason why they have the goal is that they are mostly the 3D stackable. So in case of the phase change random access memory, you already know that the Optane memory by the Intel, okay, it has the 2 floor, and it is the 4th floor is also available nowadays. So the main reason is because as a selector of the memory device, because in case of memory, we need to select only one bit among a huge density array, right? So we have to select only one cell. So in this case, selector device is required. In case of STT-MRAM, as I mentioned before, in case of the STT-MRAM, transistor is required here, transistor. And in case of transistor, it requires a lot of area overhead, like this, the gate, source, drain. However, if we are not using the transistor, but we use like a diode or the OTS, something like that, then it can be increased significantly, the density. And in case of transistor, it is also not 3D stackable. So currently, there's no any devices that is able to stack 3D using the two transistor, right? So, however, in case of the, for example, as a selector, there is the OTS. OTS is the selector used in the phase change memory. It is the 3D stackable. So, yeah, in this kind of memory, it can increase the density significantly. However, in case of STT-MRAM, it is very limited. So, the cell size is quite large. Where is it? Only the 50 F² older. So if you can see here, in case of 60 XM cell sizes at 1st nanometer, 150 F². In case of STT-MRAM, it is on the order of 50 F². But in case of RRAM or the PRAM, it is only 4 F². So size is very different. There is the different applications.
Okay, thank you for your nice response on that. Okay,